Hi everybody, this is a video for my 30SH honors pre-cal students, and we are going to start chapter 3 with quadratic functions, and we're going to start with a little review of some stuff from grade 10. The language we're going to need to use here in this chapter. And first we're going to talk about domain and range. Now remember, the domain is all possible x values, and range is all possible y values. So in the example here, where we have a parabola, we're going to write the domain and range, and we're going to use two different notations. Now in grade 10 for sure you saw set notation, but not all the grade 10 classes talk about interval notation. So set notation is kind of the classic standard, been around for hundreds of years, formal way to say the domain. Now this thing is opening up forever. Every once in a while I meet a student who thinks parabolas are like big ellipses and they're going to eventually close up. No, they're not. These two arrows, these two ends, are moving apart forever. So that means every x value possible will eventually be part of this graph. So I'm going to try to say that the domain is basically all real numbers, because the number line represents real numbers. And the way that I'm going to actually write that in my new set notation here is, or my old set notation is, I'm going to say it is x is an element of the real numbers. That's about as formal as I need set notation to be. There are more formal ways you can write it. In fact, I'll even show you. You could write down it is the set of all x values such that x is an element of the real numbers. Now, I don't need this x such that part. That's what that line up and down means. It means such that. I'm pretty happy with x as an element of the real numbers. And just so that we know that you mean business, that r should have an extra line in it. And that lets the person reading it know that you mean real numbers. Okay, in interval notation, we have to say, and you can actually look down here, oh, there's their fancy r for real numbers. That's even fancier than mine. In interval notation, you use round brackets when the value is not included, and you always use round brackets when you're dealing with infinity, because infinity is not a number you could get to. I can't walk my way down this number line and stop and say, oh, I'm at infinity now. Infinity is an idea, it's not a number. So in interval notation, I would write from negative infinity to positive infinity. Curved brackets. Now my range is a different story. In set notation, and again, forget the y such that stuff, I'm happy with just curvy bracket. Y has to be less than or equal to 1, 2, 3, 4. And again, if you don't say real numbers here, I'm assuming it's real numbers. Again, if you want the very fancy way to write that, you would write it as y such that y is less than or equal to 4 and y is an element of the real numbers. So it's basically saying starting at 4, every real number. But that says that too. We always assume you're in real numbers unless you say otherwise. In interval notation, since we're starting from negative infinity, we still say we start down forever at negative infinity. And again, notice this graph will never get higher than y is 4. So it goes up to 4, but it can hit the point 4. So square bracket. All right. So moving on. Let's try this one. Find the domain and range. Feel free to pause this video and try that for yourself. All right, how did you do? So let's see, the domain for this would be, again, x is an element of the real numbers. The range is, of course, going to be starting from 3 and up forever. So I'm going to write that as y has to be greater than or equal to negative 3. And in interval notation, of course, this would be negative infinity, infinity, and this one would be starting at negative 3 and going up to infinity. Okay, so there's domain and range. Let's talk about other things that we can find domains and ranges of. I know this chapter is going to work mainly with quadratics and parabolas, but you should understand domain and range as a concept on pretty much anything you want to apply it to. So what's the domain of this thing? Well, the domain of this thing is going to be bounded. X can be as small as negative 2. So x is bigger than or equal to negative 2. I should probably start my curly brackets. And x has to be smaller than or equal to positive 2. Or again, in interval notation, you can write negative 2, 2. Okay. For the range can go anywhere from 1 to 5. So I will write that as the y values. And yes, those arrows always have to go that way. I mean, they're not really arrows. They're less than and greater than symbols. But they always have to be pointing in the same direction as each other. So y has to be greater than or equal to 1, but it's less than or equal to 5. And again, in interval notation, you would go 1, 5 with square brackets because you are hitting those points. All right, if you are given a set of points, all you can do for domain is actually just list the set of points. So this is 2, 3, 4, 6. So the domain is 2, 3, 4, and 6. And the range is, let's see, what are all the y values here? We have a negative 3, negative 1, negative 3, negative 1, 3, and 6. I think I got them all. Now, how would I write this in interval notation? Well, actually, you kind of can't. So this is one type of domain and range where you don't have an interval, you just have a series of numbers. So you have to write it as a set. Okay, this guy. Now this one's interesting. My domain is actually two things. So my domain is, I'm going to just open a bracket and say, all right, well, I have a domain where I go from negative 3 to 0 inclusive. So from x is greater than or equal to negative 3, less than or equal to 0 inclusive. Then, use a comma, it starts up again at 2, but remember that's an open dot. We talked about this a little bit last unit. An open dot signifies that it doesn't start at 2, it starts infinitely close to 2. So the way I say that is that x then has to be greater than 2. Notice I don't put an equal to on there. And there we go. Done. And that's an arrow, so that's going forever. Done. If you'd have written this as x greater than 2 from left to right, same thing, that's fine. Wouldn't matter. How do I write this one in interval notation? I actually can use a union symbol. So that would look like this. I would say, okay, I go from negative 3 to 0 together with, union with, let's make a little space for it, together with starting at curved bracket 2, because we can't be on 2, to, of course, infinity. And infinity is always a curved bracket. Sorry I didn't give myself much room to do that. Range. So let's see, what's the range? Well, the range looks like we go down to, is that negative 1, 2, 3, negative 4? So we go from curved bracket, we go from y is greater than or equal to negative 4, and then it goes up to less than or equal to 1, together with y has to be greater than 3, right? Starting here, that's 3, yeah. So then y has to be greater than 3. And again, notice no equals here because open dot. In interval notation, I would write that as y is between negative 4 and 1, together with starting at 3 and going to infinity. All right. These are interesting graphs. We're going to see graphs like this later this year. It's a combination of two types of functions. It's a parabola, which is a quadratic function, and an absolute value function. So let's see, what kind of domain does it have? Well, it looks like, again, these arms are going that way, up forever. So x can be anything. So once again, x is an element of all reals, or negative infinity, infinity. Range, however, is kind of interesting. Notice the range is we start at 0 and we go up forever. So I would say in set notation y is greater than or equal to 0. And in interval notation, I'd say from 0 to infinity. Okay. Next, we have a list of key terms that you can research and look up for yourself. And then that's going to take us into our first video on quadratic functions. But I would like to maybe do the little bit of intro with you that's at the front of your workbook. So here's your workbook. And flip to the first page. Oh, by the way, here's where you can find all of the definitions that we just skipped in the other booklet. And let me see if I can focus that a little better. There we go. So this is a little information about something that I didn't really know existed as a serious thing until I read this page a few years ago. This is the blob jump. Now, blob jumps are interesting things. Let me just pause for a second here. Okay, here is a video of a blob jump, or sorry, blob launch. Got to use the correct terminology here. This is a blob launch. Basically, as you can see, it is a inflatable thing, great big inflatable bag of air that somebody jumps on. Somebody on the other side then gets launched. As you can see, this is quite exciting. In fact, I'm gonna play this in real time first of all. I was playing with this earlier. So in real time, here's what this looks like. Blob launch. Guy jumps, two guys jump, and they launch this individual into space practically until he splashes in the water. Now I'm gonna rewind that and pause it right there. That looks good. And I'm gonna slow it down. Slow the man down to super slow speed. And then I'm going to play it again. And what I'm gonna do, this should work. Mr. Kello is about to say this should work, is I'm actually gonna make some points here with a pen. Don't worry, I'm not writing on my monitor. I have a sheet of plastic in front of my monitor here. And I'm going to, okay, so I'm gonna, let's see, how slow did I slow this? Oh boy, that's slow. Listen to the music. Okay, anyway, this is gonna be the starting point right here. This is the head of the guy that's about to be launched, so I'm gonna put a dot there. And, uh-oh, I hope the camera goes to the same spot. Yeah, there we go. Okay, and I'm gonna just, let's see, there's a spot there. There's a spot there. There's a spot there. That looks like that's the highest he gets right there. And then now he is coming down, coming down, coming down, splash down right about there. Okay, so that's good enough. Now, hold on a second here. All right, as you can see, I've made myself a an XY coordinate grid here. And now I'm going to take this sheet of dots here, this sheet of points, and I'm going to put it on the grid. And I guess I'll start with the, I'm figuring that that blob that the guy was sitting on was somewhere in the neighborhood of about 1 meter off the water, and he splashed down there in the water, and I want the water level to be 0. So I'll just set this here, and then I'll just kind of record some points. Now I'm making some huge assumptions here. I'm doing some fast and loose with reality, but I'm going to say that since I'm assuming that that thing that the person was sitting in, it's probably a couple meters high, but he was kind of sunk into it. So I think his launching point is 1 meter. That's an assumption, obviously. But this scale is going to represent as close as I can to the real world. So what I'm going to do now is I'm going to just read all these points here. So obviously this is, where did my Sharpie go? This is the point here. That's going to be x is 0, y is 1. This would be, so let's see, the splashdown seems to happen right about there at 1, 2, 3, 4, 5, 6, 7. Looks like that's about x is 8, y is 0. And then I guess I could find a bunch more of these points. In fact, I will. I won't bore you with the details of that here. Hold on a sec. So there we go. I've labeled all the points, and it's pretty clear that this is definitely making a path that you would draw a parabola through. But I'd like to know what the equation of this parabola is. So, as you can see from my screen here, I'm going to use Desmos. And I don't know if you know this about Desmos or not, but Desmos actually does allow you to put in tables of values. So let's see, can you still see this while I'm doing this? I think you can, yep. So I'm going to ask it for a table of values, and I'm going to put in the points that you can see me doing here. So the first point I got was my launching point, 0, 1. And my second point was, I counted, now I'm rounding these as I go, about 1 and 9.5. Okay, watching me enter data is not all that exciting. Let me speed up the process just a little bit here. And there we go, I've got all my data in. And now what I'm going to do is I'm going to ask Desmos, here let me, I don't think I need my diagram anymore. Oh, no, that didn't work. Why didn't that work? Oh yeah, I know I didn't work. I want window capture up front, which it is. Hang on. Still not working. Video capture up front. There we go. Only that's not the way I wanted it to work. Okay, hold on a sec. There we go. Okay, so there is all of the dots, as you can see from my there we go. There's all the dots from my picture. And what I'm going to do is I'm going to ask Desmos to get me the closest parabola that it can, using all of its powers of computation, to these dots. So here we go. We're going to do this. We're going to say we would like y1 to be as close as possible. So approximate. And do you know what the symbol for approximate is? It's a tilde. To approximate. And you're going to learn that the standard form of a quadratic, or the general form of a quadratic equation, is ax squared, but I need to say x1 because it needs to know which data points we're looking at. Even though I only have one set of data points, it needs to be told this. To the power of 2 plus bx1 plus c. And as you can see, look at that. That's not bad at all. It comes pretty close to a nice parabolic curve. And the equation of that parabola, I don't know if you can see that. There it is. The equation of that parabola would be, here I'm going to jot it down so that we can play with it a bit. The equation of that parabola would be when a is this number, b is that number, and c is that number. So let me just get that equation down here. Okay, here we go. So that's going to be y equals, and so my a value, that's negative 1.53529x squared, and my b value is 12.5008, and my c value is negative 0.172005. Now that is, look at that, I don't even have enough room for this parabola. Let me see if I can make more room here. There we go, and then go back to this guy.